I'm Jamesina Simpson from the University of Utah, and in my talk I'll be discussing our research on studying the effects of space weather on the near-Earth environment, specifically from the ionosphere a few hundred kilometers up and above the Earth's surface to a few hundred kilometers below the Earth's surface. And the specific space weather events that we're interested in initially are coronal mass ejections. These are very major events wherein the sun ejects particles and magnetic fields. There's an image here on the bottom of the slide produced by NASA to try to illustrate this. Here's the sun right here. The blue small thing here is the Earth with the magnetic fields around it. And sometimes when the sun ejects these particles, they're in the direction of the Earth. And the largest coronal mass ejection occurred in history, and documented history, occurred in 1859. And at that time, we had telegraph operators communicating over very long, hundreds of kilometers, telegraph lines. And some of them experienced nearly fatal shocks, so they had to completely shut down all the telegraph communications occurring around the world's major capitals. Nowadays, of course, our technology has changed quite a bit, and we have a lot more technology that is vulnerable to space weather events. A much smaller scale coronal mass ejection occurred in 1989, which disrupted a lot of different aspects of our society, communications, satellite operations. It also caused a 9-hour power failure in the Hydro-Quebec power grid in Canada and upper eastern seaboard. And so what we are looking at is how our modern infrastructure can be affected by space weather events. And another reason we're interested in this is that the National Academy of Sciences came out with a report in 2008 that estimated that an extreme coronal mass ejection on the order of the 1859 event, or larger perhaps, would be very costly and could take years to recover from. That report also stated that although these extreme events are rare, they are likely to occur again in the near future. Specifically, the goals of our research are to improve our understanding of space weather hazards to electric power grids to prevent blackouts. And secondly, a rather new goal of our research is to look at the effects of space weather on electromagnetic wave propagation around the Earth up to about 20 kilohertz. And this is where Blue Waters is another area where Blue Waters has helped us in that we can increase the grid resolution sufficiently to look at these kilohertz frequency ranges for the first time. Application areas range from propagation from lightning strikes, hypothesized earthquake precursors, communications, radar, and so forth. The technique that we're using is a finite-difference time domain method, Fdtd method, and this method solves the full vector Maxwell's equations. And what I'm showing here on the lower right corner is an example grid cell in Cartesian coordinates, where we have electric E fields and magnetic H fields dispersed throughout the grid cell. Our Fdtd models of the Earth-Ionosphere waveguide have been developed over the past 15 plus years. I've listed a few of the example applications we've applied our models to on this slide, ranging from Schumann resonances to geolocation, hypothesized earthquake precursors, and so forth. Some key advantages of using Fdtd for this application is that we can include all the details of the Earth's topography, the oceans, the ionosphere, and its variation with position and altitude, and also the geomagnetic field. Also, we can model realistic disturbed ionospheric currents during a space weather event, both spatially and how they vary in time. We also have developed a magnetized plasma algorithm for the ionosphere, so we can include all the important effects of the ionosphere on electromagnetic propagation. We've generated two generations of grids, Fdtd grids. The first is formed by lines of latitude and longitude, as shown on this slide. And the grid cells are trapezoids almost everywhere, except there's a ring of triangular cells around each pole. And this diagram just depicts the grid layout. It's not drawn to scale, so all the grid cells are roughly the same size. What's unique about our grid is that the cells are merged in the east-west direction as either pole is approached, and that's to keep this grid cells from getting infinitely smaller. And this diagram is shown from a constant radial coordinate, but the grid does extend radially inward and outward from this constant radial coordinate. The second generation model we've generated is a geodesic grid that's formed by hexagons and pentagons. We got this idea from climatologists at Colorado State University. And what's nice about this is that all the grid cells are roughly the same size, and they can be equally distributed onto a processor, a supercomputer, in a very straightforward manner, much easier than the other model. Once we generated the grid, we imported the Earth's topography data. This is from the NGDC. They have it at about 1.8 kilometer resolution. And previously, we had to kind of piece together lithosphere conductivity values from around the world, where people had actually studied the composition of the lithosphere, and import that into our grid. Now, fortunately, I got a little cut off there. In 2015, there's a detailed study of the global lithosphere values and how they vary with position, and it's nice and seamless. It fits all together. So this is for the upper crust, 0 to 5 kilometers, and we can go slice through the model, and we can include all these details with depth and position around the globe, how the lithosphere electrical properties change. As we go to higher frequencies, though, above kilohertz or so, it's less important to go deep into the Earth. The electromagnetic fields decay before they go very deep. And also the computational requirements become too intensive to model into the Earth. So we can use what's called a surface impedance boundary condition, which approximates the effect of the electromagnetic wave going into the Earth's crust or the ocean. And we can use that at the Earth's surface. The magnetized ionospheric plasma algorithm, I won't be describing it in detail in this talk for lack of time, but what we need to input into that model is the electron densities, how they change with position around the globe, ions, if we account for ions as well, collision frequencies, and so forth. One source where we can obtain that information is from the International Reference Ionosphere. And here's an example plot for a certain time and date, July 2012, where we can import these values into our model ionosphere. In the rest of my talk, I'll be talking about the application of these grids to the space weather, and first to electric power grids and then to the very low frequency propagation. For the effects on power grids, one hazard that we're most interested in is geomagnetically induced currents, GICs. Essentially what we have here are currents flowing in the ionosphere about 120 kilometers up above the Earth's surface. And these can create image currents in the Earth's crust and oceans. And what I'm showing here in this image is a particular scenario where we have an ocean-continent boundary. These can pose unique hazards where we can have a buildup of currents and very high electric fields occurring at the ocean-continent boundaries. And these large currents and voltage potential differences can cause large currents to flow into the long conductors of the power grids, and they can burn out transformers. And depending on the time scale, they can burn out different components of the transformers. So we're interested in all different types of time scales for this problem. On average, about 200 days of severe geomagnetic storms occur within an 11-year solar cycle, but that can vary with each solar cycle. Up until now, approaches that have been taken to look at this problem include some that I've listed here, ranging all the way from Biot-Savart law, which is a static field approximation, to the finite element method. However, it wasn't a full-scale Maxwell's equations finite element solver. They made some approximations to simplify the analysis a bit. So all of these approaches involved localized solutions where they're modeling some region of the Earth, where they need some boundary conditions, simplified geometries such as the ones I'm showing here on the right, where they have planar layering of the homogeneous layers of the lithosphere, steady state conditions, and so forth. But we can use the results that they've obtained to first validate our Fdtd model and see what we can learn additionally using Fdtd to improve our understanding of this problem. So for an initial validation, what we've done is we've taken a Quebec, the layering under Quebec, and in the publication that was published, it's cut off on your screen there, but there's a paper by some folks in Finland. What they did was they modeled an infinite line current above 100 kilometers above Quebec, and then they calculated the electric fields at the Earth's surface and how they decay away from that infinite line current. The period that of the sinusoidal source that we're modeling is 5 minutes to match the paper. And here are shown the comparison between the Fdtd and the exact results. 0 here, it's a symmetric problem, and we modeled both sides, but I'm just showing the left-hand side away from the source. At 0 kilometers, we have the line source 100 kilometers above the Earth's surface. And you can see how along the Earth's surface the electric fields decay as you go further and further away from the infinite line source. There is a difference here between the analytical exact solutions and our Fdtd results, and that is due to the boundary condition that we had to implement in the Fdtd model. Because it's a localized solution, we had to have an absorbing boundary condition around the whole domain. And usually the boundary conditions for Fdtd work very well. You would hardly see any difference between the two, but because we're modeling such low frequencies, we need an extremely thick boundary condition. So there is about a difference of about 4.34%. The advantage of our global model is that we don't need this absorbing boundary condition along the edges, so we don't expect to see this kind of a difference, discrepancy due to the absorbing boundary condition. And we can now take this a step further and implement realistic currents in the ionosphere in a global model, not just an infinite line source. And so what I'm going to show here is a video showing over, this is what's called the Halloween storms. They occurred in October of 2003, and they caused a transformer to run out in Finland. It's just over a short amount of time, right at the peak of the storm. And so what we obtained these values from BATS-RS. It's a magnetohydrodynamic, a magnetospheric model, and they've used it for a lot of different applications. It's based from the University of Michigan. We obtained these results from Daniel Welling at University of Michigan. And so we're using these are fully three-dimensional ionospheric current systems, and we're modeling these in our Fdtd model. And so on this slide, I have on the top some early results where we have the source that you just saw from the previous slide. And then on the bottom here, I'll show the electric fields as sampled on the Earth's surface. And you will see the effects of the Earth's topography and the oceans, and how the variation of the conductivity, the electrical characteristics of the lithosphere can affect the surface electromagnetic fields during this event. So we're in the early stages of running this model, and we're going to run it over a longer period of time. And we're in the process of comparing with measurements. And hopefully we'll get our publication out soon on it. Another aspect of this work is looking at ocean-continent boundaries, where I'd shown that image earlier where we can have a buildup of currents at the ocean-continent boundaries. And at this time, there's a great concern over these boundaries, and the electric power grids actually do not know what kind of hazards these pose over how wide of an extent these amplified electric fields extend. And there's no measurements of them that I'm aware of from talking from the power grid company. And so we're trying to perform some Fdtd simulations of this boundary to see what we can learn from them. I'm showing just one example result. So there will be a poster session later today from one of my students, Santosh, and here's just one result from his simulations where he's looking at the geometry. Here is the ocean, and we're starting off. He just started this about a month ago, so we're starting off with a simple geometry. We're just the ocean and a homogeneous land, and he has a ionospheric current extending downward and coming radially downward and then across and up over this, within this range of the ocean-continent boundary. He also looked at different depths of the ocean, and you can see here at 0 kilometers on the right-hand side, you can see how there's an exponential type increase of the electric fields as we get closer to the boundary, and it can be amplified as the ocean, and what we're seeing here is the ocean depth is shallower. And what was concern of the electric power grids is if this amplification extends over broad areas, say 100 kilometers, then this can be a great concern because that can lead to large potential differences over long conductors of electric power grids. Our main focus so far has been on the electric power grids, and I showed a few early results that we're obtaining now. A second area where we've recently made great progress is in modeling very low frequency wave propagation. And we're interested in looking at space weather effects in this regime. Over the past year, we've increased the grid resolution of our model Fdtd grid on a global scale. We were at 40 by 40 by 5 kilometers a year ago. Now we're down to 1.25 kilometers, 1.25 by 3 kilometers radially. And what this does is it could allow us to, for example, model the resolution at ocean-continent boundaries that we need. Also, what it's allowing us to do is to model higher frequencies. The reason for that is that Fdtd requires about 10 to 20 grid cells per wavelength. So we need high resolutions to go to model higher frequency waves. What I'm showing here is an example snapshot after a wave. I don't know how well it's showing up, but there's a sinusoidal, like a quasi-lightning strike, but it's a sinusoidal source just initially to study the characteristics of the propagation occurring off the coast of South America, and right at this point it's propagated this far so far, and the coloring scheme doesn't show up really well on the screen here, but there's some transients from turning on the source that are excited, and these propagate differently in the waveguide between the Earth's surface and the Earth-Ionosphere 100 kilometers up. And so what we're doing right now is we're validating the model at these higher resolutions, these higher frequencies, and then we can start to apply it to different applications. So this brings me to the slide on describing on how we've really taken advantage of blue waters in our research. And so I'd mentioned that we've been able to go down to about 1 kilometer resolution. And so for the first time, we were able to model on a global scale propagation above a kilohertz. And we're shooting for going up to 20 kilohertz. And also on this electric power grid side, we're looking to look at the ocean-continent boundary effects. Other aspects that are important for this problem are regions of low conductivity rock. We can also then model the realistic disturbed ionospheric currents. And what I've shown here on the bottom of the slide is a table showing just how many grid cells we're using. So to give you an idea, at 600 meter resolution, the 1.21 got cut off, so I'll just describe the 600 meter resolution one. At one radial coordinate, we need about 1.7 billion grid cells. And so if we have, say, 100 planar layers, multiply that by 100, and that's the total number of grid cells in the entire model. Our time steps are on the order of 0.7 microseconds, on the order of microseconds or less. So our simulations are using a good chunk of blue waters. Each one, when we are getting down to 1.2 kilometers, we need on the order of 40,000 cores. If we include our magnetized plasma, we need up to 100,000 cores. Our next goal is to run it at 600 meter resolution. So we're one of the groups that's trying to use as much of the machine as possible. We've been approached by scientists at NASA's Community Coordinated Modeling Center to make our model, prepare our model for CCMC to be available to other researchers to run. At CCMC, you can request a simulation run, and so we're trying to adapt our model to be user-friendly so that others can use it to study any application they're interested in. So in conclusion, for the first time, we were able to model frequencies in the very low frequency wave range. We're modeling the Earth-Ionosphere waveguide at unprecedented resolution than ever before possible using blue waters. And future goals are to extend the model through the ionosphere. Right now we're going up to about 150 kilometers, and we'd like to go all the way up to 800 kilometers through the ionosphere. That would allow us then to couple to magnetospheric models, so that we could have a model that goes all the way from the magnetosphere all the way down, down below the Earth's surface. And finally, I'd like to acknowledge Blue Waters, DARPA and Air Force Research grants, and my NSF Career Award just ran out this last year, and then the University of Utah's Center for High Performance Computing. Thank you.